Bismillah ar-Rahman ar-Rahim. So, chapter 4, motion in two dimensions. إذا بتتذكروا chapter 3 كان motion in one dimension. وفي motion in one dimension we studied motion with constant velocity, and we studied motion with constant acceleration. And also we studied the general form of integration and derivation when velocity and acceleration are not constant, and we have a formula to represent the motion. Now we talk about motion in two dimensions. Motion in two dimensions. الحين pay attention with me for this example, لأنه everything else will depend on it. Everything else will depend on it. So I will take my time to explain it thoroughly. If you have any question, ask now, because after that we'll just assume that you understand what I'm doing. So in our motion, we start with the displacement vector, delta r. And then from the displacement vector, we have the velocity, delta r over delta t. And from the velocity, we have delta v over delta t. So everything, whatever we are going to do here will be repeated for velocity and acceleration. طيب. So let me go through it. Thoroughly. So I'll explain it one time. If you have any question, you can ask. طيب. We start with a vector r initial. I can enlarge it even more. Let me see. Okay. We start with a vector r initial. And then we have a second vector r final. Now what we are interested on is delta r. Delta r, which is r final plus minus r initial. But what is plus minus r initial? It's r final minus r initial. So this is minus r initial, this one. This is minus r initial. Okay, so let's add, let's find delta r. So r final plus minus r initial. So tail to head. This is first tail, head, and then we bring the second tail to the head as we did before. And finally, the displacement is from the first tail to the last head. So that is delta r. This is delta r. And of course, we can move this vector anywhere, still it is delta r. So eventually, this is delta r. So when we have r final minus r initial, which is delta r, when we have displacement, this is the first displacement, this is the second displacement, then delta r, which is the first displacement minus the final displacement minus the first displacement, is this vector. Is this vector. Clear? Any question? Because when I do delta V, I will not repeat this. because delta V is exactly V2, V final minus V initial.
Okay, so the delta R that we are getting is the difference, is like the displacement between if you took RF and RI?
RF and R initial. Final and initial.
Yes, so that's the displacement يعني between them?
That's the displacement. That's the result displacement.
But in the last lecture we took that adding vectors and subtracting vectors in a different way. Like why is here just like a line that connects between the endpoints?
We did that
Shouldn't
last
like
lecture. When we add vectors, we said either we do it on the graph or we do it by adding components. So this is adding
I
them.
guess it's but we're supposed to do like Ri and then Rf continues from the endpoint of Ri. Right?
No, we are doing RF plus minus RI. So we are just adding two vectors, but now the vector name is minus R. So it is RF plus minus R. So this is the first tail or R of RF, and this is the head of RF. We bring the tail of minus RI, and then we put it at the end of RF, and then we find the result. That's what we did last time using graphs.
Okay, doctor, then the result should be right.
And if you pay attention, if you want to start with R minus R initial plus RF, well, that's the one, minus R initial, and this is RF, and you end up with delta R, the same vector. You end up with the same vector. You get the point? So either minus R initial plus R final, or I final plus minus R initial will give me the same result, delta R. Yusuf said, why RI minus? لأنه delta R by definition is R2 minus R1, R final minus R initial. That by definition. Any question? Because we are going to repeat the same thing when we find delta V. So that's delta R. So in the book, what we see this, R initial, R final, and this is delta R. And this is just an explanation to show you why R initial. So in the book, we have R initial, R final, and this is delta R. And we will have V initial, V final, and this will be delta V. Clear? You need to understand this, because after that, we'll just assume that you understand it. Fine. So as I assume that no question, so it's clear. So here's what we have in the book. R initial, R final, and this is delta R. Exactly like we did in details. So now we move. طيب, what is velocity average? It's delta r over delta t, or it's the derivative, as we covered in chapter 1. But delta v, when we are talking about the average, is nothing but the vector delta r divided by delta t. And what is average acceleration? Well, it's the vector delta v divided by delta t. So as we did before, delta v is v final minus v initial. It's the instantaneous is the derivative of that vector with time, but the average is delta v over delta t. V initial is this one. Let me enlarge it a little. So this is R initial, and this is R final. V initial is the derivative of R initial, so that's V initial. This is V final, V initial, V final. So where is delta V? That is delta V. So when we have V1 like this, and V final, V initial like this, V final like that, the direction of delta V, which is the direction of the acceleration, is pointing in this direction. Of course, R is the displacement, and V is the derivative of R. When it is instantaneous, when it is average, it's delta R over delta T. Now we come back and explain what is R. R is the X component and a Y component. X component in the X-axis direction, Y component in the Y-axis direction. So this is R, this is the X component, and this is the Y component. Now, motion in 2 dimensions can be modeled as 2 independent, and this is important. This is a key in understanding motion in 2 dimensions. It is independent. Yani what's going on in the x-axis is not affected by what's going on in the y-axis. Independent. That's a 2-dimension motion, as if we are going to solve 2 problems in one. 2 problems in one. So what's going on in the x-axis does not affect the y-axis. So basically, 2-dimension motion is like 2 problems in one. Okay, well, we said the velocity, the instantaneous velocity, is the derivative of the vector r with time, but the vector r, because it's motion in 2 dimensions, then it's the derivative of the x component of the vector in the I plus the derivative of the y component with respect to time in the j. Yani, we end up with the same definition. Velocity vector has an I component and a j component. I component and j component, and we end up with the same equation that we had in 1 dimension as numbers, or as vectors in one dimension. Now we have it as vector in two dimension. Vector in two dimension. So V final is equal V initial plus acceleration multiplied by time, and all of them are vectors in two dimension. Same equation, but now we are dealing with vectors. Do we have to know how to get the final formula? No, but it's common sense. There is no derivation here. Asim, there is no derivation at all. We're just explaining that when we write this equation, you write it as one x component and y component. There is no derivation here at all. Just an explanation that now we are dealing with vectors in two dimensions. So it's not derivation. Well, it's a question that, do you understand now what's the meaning of this formula? What's this formula? Well, it's a formula of vectors in two dimensions. That's it. We didn't derive anything. If you ask, do I have to know the derivation of this formula in one dimension? Yes, you know. You have to know that. We get this from the slopes, assuming that we didn't go through that derivation because it should be simple and straightforward in the book. طيب. Now we have another equation. Remember, we wrote it before like this. That when we were talking about one dimension, now because we have a motion in two dimension, now we deal with all of that as vectors. Everything now is a vector. So instead of x, we have r. X node, we have r initial. V initial, we have it as a vector. And have a, we have it as a vector, t squared. So now we deal with the same equation, but now we deal with vectors in two dimensions. طيب, let's try to understand this equation in terms of graphs. V final is equal V initial plus AT. So this is V initial, and this is V final, the result. And pay attention, this is V initial, and this is AT, the second vector. And the result is from the first tail to the last head. That is V final. That's correct. You can write it like that. V final minus V initial is equal AT. That's correct. But like this, it's clearer that V final, this is V final, is equal V initial, which is this one, plus AT, the second vector, and then it's an addition. And in the second situation, here, R final, this is R final, from the first tail to the last head. R final is equal R initial, this is R initial. V initial multiplied by T, this is V initial multiplied by T. And this is half AT square, three vectors. We add them head to tail. And the final result is from the first tail to the last head. R final. And of course, we assume constant acceleration. Thank you for asking, Ahmed. How do you can plot distance, speed, and acceleration on the same graph? That's not the case. لأنه لاحظ, what's the dimension of R initial? Let me just enlarge it. It's meter. VT, لاحظ, meter per second, multiply by second, it's also meter. And this is AT square. Well, A is meter per second square, and T is second square, so you end up with meter. So basically, R initial is displacement, this is displacement, and this is displacement. So we are adding the three of them as displacement. Should the units, so the units should be the same? Of course, of course. Of course, even here, the unit here is meter per second. Here, meter per second square multiplied by second, so it's meter per second. We are adding the same quantities with the same units. So I hope now you have a deeper understanding when we say R initial plus VT. So this is meter. This is meter, and this is meter, and this is also meter. This is meter per second, and this is also meter per second, and this is meter per second, and this is meter. طيب, now for understanding, yes, it's for you to understand, ya Khalid. It's for you to understand. طيب. Now we come to projectile motion. Well, the good news is projectile motion is a special case of two-dimensional motion. Why it's a special case? Because we have motion in the x-axis, we have motion in the y-axis. In the x-axis, we don't have acceleration in projectile motion. So our problem now is less complicated in projectile motion. So let me repeat again. Projectile motion is a special case of two-dimensional motion. We have a motion in the x, we have a motion in the y. However, it's easier because now in the x we don't have acceleration, just constant speed or constant velocity. So let's go through it. We start with V initial. Of course, it has a component in the x and a component in the y. In the x direction, the component is the same, all the motion. Vx naught, Vx naught, Vx naught, Vx naught, always the same vector. However, in the y, we start positive, go less. At the middle of the motion, it's 0, and then become negative, and finally become exactly like the first vector, but in a negative direction. And we can continue after that. So that's the projectile motion. Yc is equal 0 because it reached a maximum height. It's like, if you can remember, we said if you understand the free fall motion, then that will help you to understand projectile. It's in the y direction, it's a free fall. Projectile motion in the y direction, it's a free fall problem. In the x direction, it's just a simple problem. We have no acceleration. So again, motion, yes, motion in 2 dimension, that's the general case. Projectile motion is a very simple case from a 2-dimensional motion. Why? Because in the x-axis, we don't have acceleration. In the y-axis, it's a free fall. It's a free fall problem. So whatever we learn in the y-axis, we are going to use whatever we learn in motion in free fall, we are going to use in projectile. So this is our famous equation. This is our final. This is V initial multiplied by time. And when we add them all, this is half G T square. Now notice that half G T square is negative because we said always G is pointing down, and here we assume that up is positive and down is negative. So here you end up with just our final. So we are adding just vectors. So doctor, the velocity of the x-axis is not decreasing. There is no point in projectile motion where the object starts free falling downward, right? I didn't quite understand you. You can use your mic to talk. However, in the x-axis, it's a constant velocity. In the y-axis, it's a free fall. It's a free fall problem. We are going to solve one problem coming soon, inshallah. So in the x-axis, so we can say this is in the x-axis and this is in the y-axis. In the x-axis, we don't have acceleration. The only equation that we are going to use is this one. X final is equal x initial plus v naught x multiplied by t. And in the y-axis, it's the equations of the free fall. It's the equations of the kinematic equations of the free fall. Because free fall, that means g, or acceleration, is constant. So we can use all the equations of the free fall. Now I have I don't know, I have a problem with the book doing all these derivations. So horizontal range and maximum height of a projectile motion. Well, the first problem is this only a special case. When y node is equal, y is equal 0. So he is doing all these kind of derivations assuming y node is equal y is equal 0. And then he goes through all these kind of derivations to reach the first equation. and then he will go another derivation to reach the other equation. And as I told you, this is also a special case. Y is equal y node is equal 0. Y node is exactly like the free fall. If you revise the chapter 3, when we talk about free fall, Y node is where we start our motion. So for me, I will not ask you for the derivation of this equation or this equation. I will not ask you for that derivation because it's a special case. And it's not that the problem, if you use this equation and this equation in a problem that y does not equal y node does not equal 0, your question, your answer will be wrong. So be careful. These two equations are a special case if y is equal y node is equal 0. And go back to chapter 3 when we solve the problem. Let me remind you, we have a man standing like this, and he throw an object up, and then the object went down. That was, we covered that in chapter 3. And we said that we choose that this is our y node is equal 0. So in this situation, in projectile motion, it's only a special case when y node is equal y is equal 0. So be careful. You cannot use this equation, or this equation unless y node is equal y is equal 0. Be careful. So this can be used only if the object ends in motion the same level. That's correct. That's correct. Yeah, man. That's correct. Yeah, man. So be careful, ya jama'at al-khair. Personally, I will not ask you for the derivation of this equation or this equation. And be careful when you use them because it's just a special situation, special case.
Doctor, it won't make a difference if it rolls in the same level as it started. It won't make any difference. Where's the special case in what we just took? Because it's the same thing as chapter 2.
No, it's not the same thing as chapter 2. No, it's different. Suppose that in chapter 2, we never said that this is y, if you still remember, and it was, if I'm not mistaken, minus 45 meter. So you cannot find anything with those equations if y is equal less or more than y node. This is just a special case.
Okay, Michel, we need to find the maximum height reached, right?
Time.
Or what do we need to find here?
Let me give you an example. Suppose that we have a situation like that, and that is your projectile. Your projectile will go like this, correct? So this, from here, to this point, this is not R max. So where is R max? According to this equation, up to here. Up to here, that is your R max. It's not the total distance, because here we assume that y is equal, y naught is equal 0. So we assume that we can calculate until this point, which is y is equal y naught, and it's equal to 0. After that, this part you cannot calculate with this equation. Also for maximum height, well, you can find this as maximum height, yes, using this equation, that is h. But if we are interested relative to the ground, you'll be in deep trouble. So be careful when you use these two equations. Assume y is equal, y naught is equal 0. Well, that's what I'm telling you. And this is a special case. This is a special case. It's not to solve any problem in projectile. Let us go through. When we take an example with numbers, maybe you'll have more feeling. Maybe you'll have more feeling for that. طيب. الحين in projectile motion, and you will see that when you do the experiment in the lab, that if the angle is 15, or the angle is 75 degrees, you end up covering the same distance. Well, here the height will be different and the time will be different. However, you will cover the same distance. And same thing goes for the angle 30 degrees and 60 degrees. You will cover the same distance, time is different, and height is different. Sine and cosine, they are not, I don't understand when you say the same. They are not the same. They are the same at angle 45. But other than that, they are different. They are different. Because the distance traveled will be the same. However, the time of travel will be different. The height of travel will be different. And we have a third one from those special angles, اللي هي الانجل 45, and that will give me maximum x اللي هي at 45. Yeah, man. What you are saying, well, let's make it clearer. Suppose that this is V, which is equal Vx I plus Vy j. So Vx component is equal V cosine theta. Vy component is equal V sine theta. So yes, if it is sine 30 and cosine 30, yeah, they are equal, but that's x component and y component. So we just switch x and y components, and we end up with the final result. And this is for those special angles. But again, you need to know that time will be different and maximum height will be different. I hope it's clear, because sometimes it's for some students it's tricky. That's correct. They have the same horizontal distance, but time and x component, y component, maximum height are different. طيب. So as I said, for these two equations, again I repeat, this is a special case when y is equal y node is equal 0. So be careful when you use these two equations. So in the x-axis, we have this equation, and the rest is for the y-axis. So x motion, and the rest for y motion. So let us do an example. First, I start with a simpler example, and then we do the example here in the book. Type. Our example, I think I need to just to leave a space. So let's say I'll start here. I'll just go up. So, hey, example. What's our example? Suppose that we have a gun, and the gun shoots a bullet. V of the bullet, V node, is equal 900 meter per second. And then you have a target. Here is the target. And what's the distance between the gun and the target? 300 meter. So first question. If you aim directly at the target, will you hit the target? Why? Why you cannot hit the target? Gravity. What will gravity do? طيب decrease the height. طيب سؤال if I use a laser pointer, if I use a laser pointer and the laser pointer just hit the middle of the target, will I hit the middle of the target? No. That is correct. And why is that? Because there is a gravity will pull the bullet down. So in reality, the motion will look like this. This is y node is equal 0. And now we have, this is my y. So the bullet will reach here. So this is my bullet. Any question before we do the calculation? طيب when you want we said that in the free fall you need y node. Where do you want to have y node? Again, it's a free fall problem. That is the starting point when we shoot the bullet. Same level of shooting. صحيح يا عاصم. Again, we are solving two problems in one. The first one is a free fall. The second one is just motion without acceleration. Pretty amazing. It is said that a bullet drops. That's correct. That's correct. And we are going to calculate that, يا يمان, إنه how much after 300 meters of traveling, how much the bullet will fall, and we will calculate it. It will be about 54 centimeter. 54 centimeter. We will come to that. It's a lot of inches. That's correct. عشان هيك يا عاصم في ناس بقضوا عمرهم في ناس بقضوا عمرهم عشان يصير قناص. To be a sniper, some people spend all their lives just to be a sniper. It's not only gravity. You have the wind speed. You have to calculate the air resistance. You have even to calculate the spin of Earth. If you shoot مثلا from south to north or north to south, it is different than if you shoot east to west. طبعا في بعض الافلام قريبه كثير لما يحكوا عن السنايبرز بتكون قريبه للحقيقه، وبتلاحظوا you'll find always if a sniper want to have a target that is very far, that he has a helper, they call it spotter, to help him measure the speed of the wind and determine the distance of the target and do all the calculation for earth spin and wind and gravity and humidity. That's correct. So we here in physics, we take it a very, very straightforward and simple situation. No friction, no spinning of earth, nothing, just a free fall problem. Yeah, Ahmed. Yeah, Ahmed said the target will run before the sniper take action. Well, it's a complicated job. It's a complicated job. But here in the class, we just do the simplest situation. The simplest situation. And derive equations. No. Nobody derive equations, Yusuf. They have tables. They have tables. After new technology, a small program on the cell phone or on the gun will calculate for you everything. Before they memorize the tables, they memorize it, that if the wind is like this, you need to move the scope by this degree. If it is this far, you need to adjust the scope by vertically this degree. But nowadays, it's very easy using technology. Very easy using technology. Yes. I hope not I convince you, Yusuf, that you go to the army and be a sniper. طيب. طيب. So now let's try to do the physics. Let's try to do the physics. In any projectile problem, you need to divide it x and y. And in the x, and the y, you need to write d, v initial, v final, acceleration, and time. And also here in d, in y, we write d, v initial, v final, acceleration, and time. Always you write those 4, 5, always in the y and the x. And then let's try to fill them. Let's see the information. D in the x-axis is 300. V initial in the x-axis is 900. طيب, what is V final in the x-axis? Same. أحسنت يا يمان. Because we said the projectile motion in the x-axis, we just constant velocity or constant speed. طيب, what's the acceleration in the x-axis? 0. أحسنت يا يوسف. طيب, can we calculate the time will take the bullet to reach the target or not? أيوة, اللي هو حكينا V is equal delta D على delta T So delta T is equal delta D على V, which is 300 divided by 900, which is 1/3. So that's 333 seconds. Clear how I got delta T? طيب, now this will help us in solving the problems of projectile. It's also the same time. Why it's also the same time? Well, if the bullet reached the target, that means projectile motion is over. So whatever time is traveled in the x-axis, it is the time traveled in the y-axis. Clear for this point? طيب. Let's see the other thing. So let's try to find D. D in the y-axis. D in the y-axis. Well, it's a free fall. It's a free fall. Y is equal y node plus V node multiplied by T plus half AT square. That's a free fall, a problem. That's a free fall problem. So Y is equal, what's Y node? 0. V node in the Y. What is V node in the Y? It's a 0. It's a 0 لأنه for the bullet it is like a free fall problem. It will start from 0 in the Y and then it will start to accelerate downward. طيب, plus half. What is G? Plus 9.8 or negative? أحسنتم. أحسنتم. And what is T? Well, we just calculate it. Square. So right away you will realize that Y will be negative because in free fall we said this is Y node, up is positive, down is negative, and G always pointing down. So calculate it for me. What's the Y distance for the bullet? Can somebody help? We are calculating what now? We are calculating the Y. We are calculating how much the bullet will go down below the target. Y V node is equal 0 لأنه it's a free fall. يعني what was the initial speed of the bullet when it went out of the gun? The Y speed. For Ahmed, I'm talking for Ahmed. Well, if you are talking about the Y component of the velocity, it was 0 in the Y. Okay. So كم what's the distance? Yeah, minus 54 of a meter. What's the meaning of minus? That means it's below y node. Below y node minus 54 centimeter. So here we come and put minus 54 centimeter. Well, 54 or 0.54 is the same. V initial is 0 because it starts from 0 in the y. طيب, what's acceleration? Acceleration is minus 9.80 meter per second square. طيب, can we calculate V final? Y is the position that the bullet will reach. That's correct. Below the target. Below the target. Now the question, can I calculate V final in the Y? Of course I can. Well, V final square is equal V initial square plus 2A and multiply by Y. So V initial is 0 plus 2 multiply by minus 9.8 multiply by minus 0.544. Yes, it should give the same answer. It should give the same answer. And after we finish this, we can use V is equal V naught plus 80. Now, pay attention that here is minus and here is minus, so the result is positive. If you do a mistake in the signs, you will have V square is equal negative number, and when you put it on the calculator, it would give you an error. It will give you an error. So what's this number? $10.66. Be careful, ya Muhammad. Be careful, ya Muhammad. So that means V final is equal to answers 3.27 meter per second, or could be minus 3.27 meter per second. Which is the answer, minus or plus? Of course, it's a minus, because now the bullet is going downward, so it's a minus. طيب, let's try to solve it. تفضل.
Why is the V initial 0 though?
That's the Y, in the Y. That's a threefold problem.
Yeah, okay.
طيب, V final is equal V initial plus, let's call it V initial, plus AT, that is equal 0 plus minus 9.8 multiply by 0.333, and what will be the answer? It should give me the same exact answer. So by using this equation, I'm not confused. Right away, I have a negative answer. But if I use this equation, I need to be careful, because the sign means the direction. And we are dealing with vectors here. So if you write the velocity is 3.27 positive, the answer is wrong. The answer is wrong because the minus sign is very important. Any question? طيب. I'll stop here and let you digest what we said. And inshallah, in our next lecture, we will do this example. We will do this example. I'll just put a line for next lecture, inshallah. Doctor, it's minus because it's down. Exactly. It is minus because we assume downward is negative. Because I can solve the whole problem and assume downwards is positive, and it will give me the same answer. So let me emphasize this again. Gravity is always pointing down. Now it's your choice to choose up is positive, down is negative, or it's your choice to say down is negative, up is positive. It's your choice. But in all cases, gravity is pointing down. So sometimes you can assume down is positive, up is negative, depending on the problem. Sometimes you can assume up is positive, down is negative. Let me stop recording and then